In our last video, we talked about particle equilibrium and 3D force vector systems, which explored different operations that must be conducted on vectors to achieve a Cartesian form of forces, to find unit vectors, and to also find angles that a vector may make with the other axes of a system. We also talked about dot product as well as projected forces, and talked about the different kinds of forces that we might see in a problem like this. So this problem here, we're going to go through a couple more problems today. So for problem 3, we are given a 2D problem where we have a spring, which is where we have a force pulling ring B in one direction, being held in tension by a spring, and two cables in tension pointing away from B as well. So if we were to draw a free body diagram for B, so we want to select B as our free body diagram because it's got the most stuff happening to it, right? Because there's this force, FBC, and we know that cables are in tension, so we want it to point away from our point B. And we have FBD, and then we have FBA, which is held by a spring. So we're going to have to be using our equations for force from a spring, which is F equals K stretched minus unstretched length. Okay, so what are we given? We are given our spring constant. We're also given our unstretched length, and then our stretched length, which is given here. So determine the forces in FBC and FBD in the position shown. Okay, so let's decompose this. So the way I'm going to decompose into X and Y components. So I'm going to decompose. So let's outline some geometry. So this is 300 millimeters, this is 400 millimeters, and a base for both of them of 400 and 500 here. Okay, so now we can start. So I am going to start with our spring, and it's only in the X direction, so there's no Y component. So that is going to equal to 800 Newton meters. Then our stretched length, which is 500 millimeters. So that's 0.5. Minus our unstretched length of 200 millimeters. That's just going to equal 0.5 minus 0.2 times 800, which is 240 newtons. And this is in our negative X direction because it's pointing to the left because it is in tension. Okay, next we are going to work with FBC. So if we were to find the X direction, that means we would take our magnitude of FBC, and then we would take the ratio that it makes. So then this would just be cos 45, right? Because we have the equal base and height, that means this angle is 45 degrees. Okay, and let's do BCY, which is FBC sine 5, and both these components are in positive x and positive y directions. Now let's look at FBD. FBD has a positive x component, a negative y component, and it has 400, 300 here. That means this angle here is going to be tan inverse 300 divided by 400, opposite over adjacent, which is 36 degrees, 36.86 degrees. So then that means our BDX is equal to FBD cos 36, and then our BDY is negative FBD sine 36. Okay, so what can we do now? So now we're going to add up our components. So we know that because of particle equilibrium, we must ensure that our sum of x components is 0, and then our sum of y components is equal to 0. We have two equations and two unknowns, so we can solve for what we need to. Okay, so let's start with Fx. So from our spring, we have negative 240 newtons. From FBC, we have positive FBC cos 45. And then we have plus FBD cos 36.86. So let's simplify this down. Let's move 240 over here. And then this is equal to FBC cos 45 plus FBD cos 36.86. And let's isolate for one of our variables. So let's choose whichever one you like best. Equals FBD. That means we would divide this by cos 36.86. So this is our first equation. And then when we solve for our sum of Fy, and that would be, so we have nothing for our spring, so then we just have FBC sine 45 minus FBD sine 36.86. To move one over, so then we'll do FBD sine 36.86 equals FBC. Then that's over sine 45. And then we're going to plug this value into our second equation. So then what does that give? So put that in for FBD. So that's 40 minus BC cos 45 Okay, so that gives us, so I'm going to rewrite this so it's more clear. So that's subbing in for that value. We still have sine 36.86 for sine 45 equals FBC. Okay, let's keep going. So yeah, okay, so then that will give us sine divided by sine 45. Okay, and then let's move that to the other side. So let's move this here. 240 times. So then we're going to distribute that into there. So this is 203.6467 minus FBC cos 45 times. So then this is 0.6 equals FBC cos 36.86. Okay, we're going to add that. So cos 36.86 plus 0.6. So that's 203.6467 equals FBC 1.4. Then we're going to take this value here, then divide it by 1.4. FBC is equal to 145.46 newtons. Then when we plug this back in to our equation 1, so 240, then our newfound value of FBC cos 45 over cos 36.86 equals FBD. So that's 240 minus cos 45 divided by cos 36. And that gives 171.428 newtons. All right, so that is how to solve 2D particle equilibrium given cables and spring systems. Okay, and next question is also a two-dimensional problem. So determine the maximum mass of the lamp that the cord can support so that no single cord develops tension exceeding 400 newtons. So for this question, we are going to want to split up our free body diagrams. So we want to find the mass that our lamp can have, so then we don't have any tension developed that exceeds 400 newtons in our cables. So if I were to divide it, I would use this and this half. So let's start with our ring C in red. So this is C, it's a force FCD, giving tension that way. This is FCA, 435, and we have FCB. So let's make our x and y equations for this half. So we have x equals 0, which is equal to FCA (3/5), and that's in our negative x direction, going that way. And we have, minus FBC, then that's, actually no, sorry. Before we do that, I'm actually going to write the other free body diagram first. So FCD also points away from our D ring to create tension. This is FDE. And our force of weight, which is just mass times gravitational force. Okay, so actually I'd like to start with our right side free body diagram first. So let's make our equilibrium equations. So we want negative FCD. Generally because there's just a lot less going on this side. That's in our negative x direction. Then this is plus FDE cos 30. In our FY direction, we have negative gravitational force or negative weight. And our y component of FDE is positive, so then that's plus FDE sine 30. So you can see that FDE is common for both equations. So let's isolate, So let's isolate FDE and then plug to find our other value, which is FCD. Okay, so let's work with that. This is still part 2. So in our Fy equation, mass times gravity, we move this to the other side, divided by sine 30 equals FDE. We will be answering in terms of m because we don't know what our mass is yet. So we're going to keep that as a variable. So we'll do m. So this is from equals, no, hold on. 9.81 sine 30 equals FDE. Then FDE is equal to, so that's 9.81 divided by sine 30, 19.62 m. And then let's plug that in for our Fx equation. So FCD is equal to FDE cos 30. So times cos 30. FCD is equal to 16.991 m. So to recap, we kept everything in terms of mass, we kept that in there. We knew that FD was common for both equations, so we wanted to isolate for one and then plug it into the other to find FCD. Okay, so now looking at our other free body diagram, now that we know what FCD is, there's a little less going on. So I'm just going to zoom out a little bit so I can see and write. So our sum of fx equals 0, so that's positive FCD. That's negative x component of our FCB cos 45, and FCA in our negative x direction, FCA, and then we'll just use our ratio instead of our angle, do 3/5. All right, and then for our Fy equation, we have both positive and negative. So we have positive FCA and we have minus FCB sine 45 equals 0. So now we're going to plug in for the values that we know. So let's start by plugging in FCD in our Fx equation. So I'm just going to draw an arrow to show our work. So then this is equal to 16.991 m minus FBC cos 45 minus FCA 3/5. Can isolate for, so both FCA and FCB are common between them, so you could choose whichever one you'd like to isolate for. Over cos 45. Then we have so we're going to keep that for our FBC. So then when we plug this into our Fy equations, so then we have FCB 45 sine 45 equals FCA 4/5. We're going to plug this in now. So then this will give FCB this will give 16.9191 minus 3/5. Let's just simplify that. So 0.6 FCA cos 45 times sine 45 equals 4 divided by 5, 0.8 FCA. Okay, let's move some things around. So then let's distribute this sine 45 and move that cos 45 over there. So sine 45 times, so then this is 12.0147 minus 0.6 times sine 45, 0.42426 equals 0.8 times, we're going to move that cos 45 over, 0.8 times 0.6 times 0.6 times 0.8 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 times 0 0.5656 FCA. I forgot to put FCA over here. So then we move that around. You're going to get plus, so you have 12.0147 M equals 0.9899 FCA, and FCA is going to be equal to 12.1367 M. Okay, and then we're going to put it back into this equation for FBC, and FBC is equal to 16.991 M equals, I'm going to substitute our value for FCA, so it's 12.1367 cos 45. FBC is equal to 16.991 times, minus answer for FCA times 3 divided by 5 divided by cos 45. FBC equals 13.7305 M. Okay, so now that we've done that, we've solved for all of our forces in our cables, with each of them being in terms of M. So we want to find the largest one because we want to maximize our system, because we want the maximum mass we can have. So we want to find the force that has the largest coefficient. So in that case, we are going to take a look at FDE. So all forces in terms of M. So use largest magnitude to maximize mass. So with our FDE, we're given 19.62 M. And we know that our maximum force that we can have is 400 newtons. So that gives us M is equal to, so it's 400 newtons divided by 19.62, which is going to be 20.387 kilograms as our maximum weight of our lamp. Right, so if you have a question that has multiple opportunities for a free body diagram, so if you have 2 points of connection that are connected themselves, that is a good place to split them up, right? So just make sure when you're drawing your free body diagram that your cables are always in tension. So that means they should be pointing opposite directions depending on which free body diagram you drew first. Okay, question 5. So this is a 3-dimensional problem. In this last question, we have a slab that is being suspended by 3 cables, which are attached to the ring at the top, and we want to know the tension of each cable. So we're going to need 3 equations for our particle equilibrium, one in the x direction, one in the y, and one in the z direction. We have 3 unknowns, so that means we can solve for this. Okay, so I'm going to color code them. So this is AB. Orange we will have C, and AD in green. Now notice that all of these, since they're in tension, all of them are pointing down, so it's going to have a net downward force from our cables. But since our system is in equilibrium, that means our plate will have to exert a force to resist it. Right? And this can be explained with Newton's third law of gravity. For every action, there's an equal and opposite reaction. So even though your intuition is telling you that, hey, the plate is weighing down this way, because of the point we're measuring it at A, because at A we are being pulled down by our tension from our cables, that means we would need to have this to resist it in order to create equilibrium. Okay, so this is similar to what we did for our first problem. So let's write it out. So for A, we are at a height of 12 meters in the origin. B, so let's call this negative direction this way, positive direction this way for our x, and let's call this positive, and let's call this negative direction. So then B has no height. We are measuring 6 meters on our x-axis, the negative direction. And in our negative y direction, we are at -6. Sorry, give me a second. Sorry, this isn't -6, this is -4. Because 6 is our whole length, and then we are measuring 2 from the end, so that makes this 4. Okay. For C, we have, so we are all the way at the edge, so that means we are going 6 in our x direction, that way, in our positive x direction, and we are going so our total length is 12 of our sides. It's 2 from the end, so that is 12 minus 2, that's -10. No, hold on, sorry. That's -4. Yeah, okay, sorry. And so you have to be careful when you're first setting this up. You have to make sure you're looking carefully, so don't rush it. Okay, and point D is in our positive x direction of 4, positive y direction of 6, and 0. Okay, right on. So these are our points, and we are going to start making some equations for them. So let's do A first. So we want the position vector. So that is pointing from A to B. So that means we are going to be doing -4 minus 0, I. That's -6 minus 0, j. Let's put 0 minus 12, k. This is going to equal -4i, -6j, minus 12k. It's AB done. Let's do AC now. So this is 6 minus 0, I. This is -4 minus 0, j. And this is 0 minus 12k, which is equal to 6i minus 4j minus 12k. Lastly, we'll do AD, which is equal to 4 minus 0i plus 6 minus 0j plus 0 minus 12k. This is 4I plus 6j minus 12k. So now we're going to want to find the unit vectors. Just going to move this over. Oh yeah, and lastly, we should also define our weight, which is in the positive k hat direction, because it's pointing directly upwards from the z-axis, and that is just mass times gravity, and we know this to be, it's 150 kilograms times 9.81, which is equal to 1471.5 newtons in our k hat direction. Okay, so now let's find our unit vectors. It's going to be negative 4I minus 6j minus 12k over 16 plus 36 plus 144 is equal to equal to 14, so that's negative 4 over 14I minus 6 over 14j minus 12 over 14k. Hopefully this isn't too fast for you. So then we're going to take our AC, so minus 4j minus 12k, and over square root of 16 plus 36 plus 144, which is also equal to the same thing. So that's 6 over 14I minus 4 over 14j minus 12 over 14k. Last one. And like all of these have the same things that make it up. There's 4 in each one, there's 6 in each one, and there's 12 in each one. So let's just skip a couple steps because we know that our denominator is going to be 14. So this is 4 over 14I plus 6 over 14j minus 12 over 14k. All right, so now we're going to define our force equations. Which means that for FAB, that will be our magnitude of FAB times what we found for our unit vectors. And so forth. So FAC equals magnitude of FAC times 6 over 14, negative 4 over 14, minus 12 over 14. FAD is equal to FAD magnitude, that's 4 over 14, 6 over 14, and negative 12 over 14. Okay, so now let's do our equilibrium equations. All right, so our sum of our fx equations is equal to 0. So then we're going to take negative 4 over 14 FAB. That's plus 6 over 14 FAC. So basically we're just taking each separate component. And that's plus 4 over 14 FAD. For our sum of our y, we will have negative 6 over 14 FAB, negative 4 over 14 FAC, and then that's plus 6 over 14 FAD. And lastly, for our z direction, so that's equal to negative 12 over 14 FAB, negative 12 over 14 FAC, negative 12 over 14 FAD, and don't forget we have a positive direction for our weight that opposes it, which is 1471.5. Newtons in our k direction. So that was our opposing weight force. Okay, so choose anyone to start with, and you're going to isolate for one variable. It's going to be in terms of 2, then it's going to be in terms of one variable, then it's going to be, you're going to be able to solve one and then work backwards to solve the rest. So let's start with, I'm going to start with 3 because I think it'd be fun. So let's do just that. So let's move everything over. So that's 12 over 14 FAB plus 12 over 14 FAC plus 12 over 14 FAD equals 1471.5. I'm going to take 12 14ths out, so then that's FAB plus FAC plus FAD, 14,000. Okay. And then we can move that over, so we can take 147.5 multiplied by 14 divided by 12. So then FAB, FAC plus FAD is equal to 1716.75, and isolate for whichever one you'd like. So I'm going to start with FAB first. And that's 1716.75 minus FAC minus FAD. So that's our first one. So now we're going to plug it into our second one. Okay, so that's going to give, so I'm going to factor out 1 over 14. So that's negative 6 FAB minus 4 FAC plus 6 FAD is equal to 0. Okay, and I'm going to plug in for the value that we just found up here for FAB. So this is negative 6. Then I'm going to plug in. This is 1716.5. minus 4 FAC plus 6 FAD. Okay, we're going to distribute this number in, so then that's negative 6 times plus 6 FAC plus 6 FAD minus 4 FAC plus 6 FAD. Okay, so that's negative 0. We can add our FAC terms together, so that's plus 2 FAC. And then that's combining our AD terms, that's plus 12 FAD. Okay, and let's distribute that 1 over 14 in there. It's equal to negative 735.75 plus 2 over 14 FAC plus 12 FAD over 14. Okay, still a little more to go. Hopefully you're following along. 0.75 equals, I'm going to factor that out again. That's 2C plus 12 FAD. And let's multiply this by 14. So that's going to give I could have just used that step. I'm not really sure why I didn't. Okay. So now I can do this. Minus 2 FAC over 12 equals FAD. And now we're going to move on to our first equation, and we're going to plug in for both of those values. So I'm going to just find another piece of paper up here. Oh, do I not have one? Okay, that's fine. That is fine. Okay, let's see how far we can make it. Okay, so this is 0 equals negative 4 FAB plus 6 FAC plus 4 FAD. And this is going to let us solve for FAC first, I believe. Okay, so if we were to multiply that to the other side, this we can just factor out to be 0. So 0 equals negative 4 FAB plus 6 FAC plus 4 FAD. And we're going to plug in for what we know. So negative 4 FAB we found to be 1716.75 minus FAC minus, and we know FAD is equal to for 12. Oh no, there's no more room. Okay, it's okay. Plus 6 FAC plus 4, and then plug FAD again. 0.5 minus 2 FAC over 12. Okay, I'm going to move this up. Just going to write this down so I can transfer it. Okay, and now we're going to just transfer this over. I think I have a blank piece somewhere. Okay, let's just use this one. We don't need these notes anymore. Whoever said we needed these? Okay, so I'm just going to clear this page. I can use this one next. Okay, so again, we had plugging into our first equation, negative 475 minus FAC minus over 12 plus 6 FAC plus 4 or 12. Okay, so lots of distributing to do. That all belongs to one thing. Okay, so I'm going to try just simplifying this first. So let's do 1716.75 times 4. So negative 6867 minus 4, sorry, plus 4 FAC plus plus 6 FAC plus 4 times 1035 minus 8 FAC over 12. Oh, okay, this one's a lot. 6867 equals 4 FAC plus 4 times 5 divided by 12, 3433.5 minus 8 over 12, 0.6667 FAC plus 6 FAC plus 1202 divided by 12, 3433.5 minus 0.6667 FAC. So then totaling up our FACs, we have got 4 minus that one plus 6 minus this again. That's 8.6667 FAC. Then 3433.5 times 2. Then we have plus 6867. Those are going to cancel out. And then is FAC equal to 0? Okay, phew. Okay, I thought I did something wrong. Yes, okay, FAC is in fact equal to 0 newtons. So then when we plug this back in to the other equations we made, now going backwards, so from 3, we know that FAB is equal to no, we should do the other one first. Sorry, plugging into equation 2 again, we know that FAD is equal to 10300.5 minus 2 FAC over 12. So this is just going to equal We plug in for 0. So 103. 103.5 divided by 12 is 858.375 newtons for FAD, and for FAB is equal to, so minus FAC minus FAD is equal to minus 0 minus 858.375 is minus 858.375 newtons. Okay, and that is that problem done. Let's check our answer. Awesome, okay, great. Okay, so that brings us to the end of problem 5. It was a big one. Yeah, so those are some practice problems for static equilibrium in 2D and 3D spaces. I hope you guys enjoyed. I hope you guys were able to follow along. And yeah, I hope this clears up any difficulties that you have with these questions. These were some harder problems. So definitely, you have the skills that you need to solve these problems now. Thanks for watching.